Welcome to this fascinating exploration of the popcorn paradox. Today we're going to investigate how water, trapped inside a kernel, becomes the explosive agent that creates popcorn, even when we're cooking in dry oil. Let's start with a fundamental question. Why does popcorn pop? And more intriguingly, why doesn't heating with perfectly dry oil pop the kernels? The answer involves understanding phase transitions, pressure buildup, and the unique structure of popcorn kernels. Let's first examine what's inside a popcorn kernel. Every kernel contains three essential components. The outermost layer is the hard hull, which acts as a pressure vessel. Inside is the starch layer. At the very center is a small amount of water, typically around 14% by mass. That 14% water content is absolutely critical. Too little water and the kernel won't pop too much, and the hull ruptures prematurely. Now let's understand the physics. When we heat a popcorn kernel, what actually happens? First, the temperature rises from room temperature, about 25 degrees Celsius, up to 100 degrees Celsius, the boiling point of water. At 100 degrees, the water desperately wants to become steam, but it's trapped inside the hard hull. As we continue heating past 100 degrees, the pressure inside starts building dramatically. We can understand this using the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles times the gas constant times temperature. Let's calculate how much pressure builds up inside a popcorn kernel. This is where the science gets really interesting. Popcorn typically pops at around 180 degrees Celsius, which is 453 Kelvin. Here's a question for you. If the volume stays roughly constant, how much does the pressure increase as we heat from 25 degrees to 180 degrees? Using the ideal gas law, the pressure ratio equals the temperature ratio. 453 divided by 298 gives us about 1.52. But wait, this is just the thermal expansion of gas already present. The real pressure increase comes from the phase transition of water to steam. The phase transition from liquid water to steam is where the explosive power comes from. When water transitions to steam, it expands by approximately 1,600 times in volume. Here's a visualization. A small droplet of liquid water expands to 1,600 times its original volume when it becomes steam. Inside the kernel, this creates a pressure of approximately 9 to 10 atmospheres before the hull finally ruptures. That's 9 to 10 atmospheres, or about 900 to 1,000 kilopascals of pressure. Now let's address the paradox. Why can't perfectly dry oil pop kernels, even though the oil can reach temperatures above 180 degrees? The key insight is that oil provides the heat energy, but it cannot provide the explosive agent. The explosive agent is the water vaporates. If you take a kernel and completely dry it out, then heat it in oil to 180 degrees, nothing happens. The starch might gelatinize, but there's no explosion. Without internal water, there's no phase transition to create the massive volume expansion and pressure buildup. The oil molecules are too large and nonpolar to penetrate the hull and replace the water that was inside. Let's do an energy analysis to understand how much energy is involved in popping a single kernel. The total energy Q equals the mass times specific heat times temperature change, plus the mass times the latent heat of vaporization. First, we need to heat the water from 25 degrees to 100 degrees Celsius. For a typical kernel with 0.02 grams of water, that's about 6.3 joules. Next is the phase transition energy, which is much larger. The latent heat of vaporization is 2260 joules per gram, so for 0.02 grams, that's about 45 joules. The total energy is about 51 joules per kernel. For 50 kernels, we'd need about 2550 joules, which is 0.7 watt-hours. This popcorn mechanism has fascinating analogies to other physical systems. Let's explore some of them. First analogy, a pressure cooker. Like a popcorn kernel, a pressure cooker uses a sealed vessel to trap steam and build pressure. The pressure cooker traps steam to raise the boiling point of water, allowing food to cook faster at higher temperatures. Second analogy, volcanic eruptions. Magma contains dissolved gases, similar to water in a kernel. As magma rises toward the surface, pressure decreases, and dissolved gases explosively expand, causing violent eruptions. Third analogy, opening a champagne bottle. Carbon dioxide is dissolved under pressure. When you remove the cork, pressure drops instantly, and carbon dioxide rapidly expands out of solution, creating bubbles and the characteristic pop. The common principle in all these systems is a fluid trapped under pressure that suddenly expands when the container fails or opens. Let's discuss why the hull strength is so critical to the popping process. Here's a question. What happens if the hull is too weak? If the hull is too weak, it ruptures before sufficient pressure builds up. The result is a partial pop or no pop at all, just a sad deflated kernel. And what if the hull is too strong? If the hull is too strong, the kernel might burn or char before the pressure becomes high enough to rupture it. The stress on the hull follows the thin-walled pressure vessel equation. Sigma equals P times R divided by 2T, where P is pressure, R is radius, and T is thickness. Typical popcorn hull thickness is 50 to 100 micrometers, perfectly engineered by evolution. Let's walk through the complete sequence of events during popping, frame by frame. At time 0, we have a kernel at room temperature and atmospheric pressure. After about 60 seconds of heating, temperature reaches 100 degrees and pressure is around 3 atmospheres. At 90 seconds, we're at 180 degrees and 9 atmospheres. The hull is under extreme stress. Then in a fraction of a second, the hull ruptures explosively. Steam expands violently, turning the kernel inside out and gelatinizing the starch. The entire expansion process happens in less than 1 millisecond. That's why we hear a sharp pop sound. Understanding this phenomenon has implications far beyond making a snack. In food science, this principle is used in puff cereals, rice cakes, and other expanded grain products. In materials science, understanding pressure vessel failure is critical for safety in pressure tanks, pipelines, and reactors. In geophysics, similar principles govern geysers, volcanic eruptions, and hydrothermal vents. For a more rigorous treatment, we can use the Clausius-Clapeyron equation to predict vapor pressure at different temperatures. The natural log of P2 over P1 equals negative L versus over R times the quantity 1 over T2 minus 1 over T1. Using this equation, we can predict the vapor pressure of water at 180 degrees Celsius. At 180 degrees, the vapor pressure of water is approximately 10 atmospheres, which matches our critical pressure. Let's look at what experiments have revealed about the popping process. High-speed photography shows that the hull rupture typically initiates at the weakest point, often near the tip of the kernel. The starch gelatinizes and expands in under 10 milliseconds, creating the familiar white fluffy structure. The overall volume expansion from kernel to fully popped corn is 40 to 50 times. Let's address some common misconceptions about popcorn. Myth 1. Oil is necessary for popping. False. You can pop corn with hot air alone. The oil just helps with heat transfer and adds flavor. Myth 2. All kernels pop at the same temperature. False. There's variation based on moisture content and hull strength. Myth 3. Old kernels pop better. False. Old kernels lose moisture and pop poorly or not at all. So what conditions give us the perfect pop? Optimal moisture content is 13.5 to 14.5% by mass. Optimal temperature range is 180 to 200 degrees Celsius. Optimal heating rate is 10 to 15 degrees per second. Too slow and moisture escapes. Too fast and uneven heating occurs. Let me summarize everything we've learned about the popcorn paradox. Water inside the kernel is the explosive agent, not the heat source. The oil or hot air provides heat, but cannot substitute for internal water. The phase transition from liquid to steam creates a 1600-fold volume expansion. Pressure builds to 9 to 10 atmospheres before the hull ruptures. The hull acts as a pressure vessel, maintaining integrity until critical stress is reached. This mechanism has analogies in volcanic eruptions, geysers, pressure cookers, and carbonated beverages. The complete physics involves thermodynamics, fluid mechanics, material science, and phase transition theory.